G'day viewers. In this segment we'll talk about how signals propagate over wires and other kinds of media. This will take us one step closer to understanding how to send information across wires. Okay, here's the context. I think you've all heard me talk about this before many times. So on the left and right we have computers, which are really just sending bits. That's what we want, at least, from our links. But across the link they're sent as analog signals. We know that. We've talked about different kinds of media. Now, this means that we're going to need to represent bits as signals. To do a good job of that, we need to understand what happens to these signals as they propagate across media. That is our focus in this segment. Well, one of the first things we need to know is that signals in time can also be represented in a frequency space. Here's our signal over time on the bottom left. You can see I'm just tracing over it here. Here's this signal. This is how we're used to thinking of a signal as going up and down and changing over time. Now, it turns out that that signal can be represented equivalently, so you can map back and forth, to a representation that describes the amplitude and also phase of different frequency components that are at harmonics. This first frequency component is a fundamental wave that oscillates maybe over the time period of the whole signal here. This second one, labeled 2, the second harmonic, means to add a component which oscillates twice as fast and with a higher amplitude. Then we're going to add another component which oscillates 3 times as fast with a smaller amplitude, and so forth. If we sum up all of these different oscillating frequencies, then, believe it or not, we'll get this equivalent signal on the left. This equation here, I'm just going to write OK to forget. I want to show you this equation. This equation sort of tells you how all of the different components of the frequency harmonics can be summed up to provide the original signal. But you don't need to remember the details of that. The important point for you is to remember that this mapping exists. This is actually a tool called Fourier analysis, which is widely used in electrical engineering. So any of you who are studying that subject, you can expect to get a lot more depth about frequency space representations. The key issue for us is what happens to different frequencies as you send a signal across a media, like a wire. As you lower the bandwidth, there's a pronounced effect. As you lower the bandwidth, this means that fewer and fewer frequencies can get through, only the lower frequencies which oscillate less quickly. So you can see here in this box lost, I've taken the signal from before and I've scrubbed out all of the frequency components over 8 times the fundamental. This means that the components that I have left can only make transitions less rapidly. The effect is that our signal, which used to be this beautiful square signal that I'm drawing over here, has become more rounded. It's become this signal that we have left here. Why? Well, because when we threw away those higher frequency components, we lost a lot of the sharp corners. As you degrade further, as we lose more bandwidth, you can see that the signal here on the left becomes even more rounded. It's barely recognizable. And as you go down further, well, I can't even really make out that signal, whether it was a 1 or a 0. By the way, here's a question for you. Out of these 3 different channels which provide different amounts of bandwidth and effects on the signal, A, B, and C, which one do you think is good for data communications? Think for a moment. The answer is probably likely to be B is best. Why? Well, because we can usually make out whether the signal is a 0 or a 1. It's high here. 0, 0, 1, 1, 0. If those are the original values which were sent and we can recover them at the other end, then we've done a good job of using that bandwidth. We actually didn't need the higher fidelity signal. In a sense, we were wasting bandwidth. Now, of course, if you had an analog application like listening to a stereo, you want the higher fidelity signal or it will sound terrible. Okay, so this last bit that we learned, that fewer frequencies degrade the signal by making it transition less rapidly and getting more rounded, is key to understanding what happens to signals as they pass over a wire. In fact, I can now tell you that there are roughly 4 rough effects here that happen as the signal propagates across a wire. First of all, it's delayed because it takes a little while for the signal to propagate, as we heard before, so a fraction of time will pass. Next, the signal is attenuated. Over a wire, a signal might go from meters through to kilometers. And the electrical signal that's going to come out the other side will be smaller in magnitude than what you put in, because some of it will be lost, some of the energy will be lost. The signal will also be attenuated or more rounded because not all frequencies will be passed through. A wire tends to pass frequencies well up until a cutoff frequency, and after that frequency the signals are fairly highly attenuated. They're mostly lost, as in our example. And finally, some noise is going to be added to the signal. Just thermal noise in the receiver, that's the sort of thing that you can't get around. And if the signal is very small, this noise will end up causing errors. I'm going to show you pictures of these effects in just a little while. We'll make them up. Before I do that, I just want to point out the information in the box here. Interestingly, the EE and the CS community have different ideas of what bandwidth actually is. In terms of the EE community, bandwidth is literally the width of the frequency band. So on a frequency diagram, some of the diagrams from before, we saw a range of frequencies. The width of frequencies a wire passes is its bandwidth. So it's measured in hertz. In the CS community, bandwidth is regarded as the information carrying capacity of a link. It's given in bits a second, megabits per second. We might talk of that as bandwidth. This is really, these two quantities are really related, because if you have more EE bandwidth, you'll be able to get a link which sends information more quickly. It will have more CS bandwidth, so they're certainly related, but they're not quite the same thing. So you need to be careful who you're talking to understand what they mean. Okay, so let's see those effects. Imagine that the signal on the left is sent. What's going to happen to it? Well, one of the first effects is that it will be delayed, but we're not going to picture that because I can't draw a time delay. Then it will be attenuated. What will that look like? Well, a smaller version of the signal will come out the other side. Now the bandwidth will be limited because we go through a wire and the high frequencies won't be passed. What will that do? That will make it more curved, so we'll get something that might look more like this. And then finally, we show here that noise is going to be added. What will that look like? Well, instead of being smooth, the signal may go something like this. It's still rounded, but it has all of these jaggies on maybe, because there's a little bit of noise. You can see here the amount of noise is small, so I can still see the signal very clearly. If the signal had been greatly attenuated, then the noise would be a larger component of it. Okay, so what about fiber? Well, I don't have much to add about the transmission mechanisms over fiber. Rather, the important differences in sending signals over fiber compared to wires have to do with the physical characteristics of fiber. This graph here, this figure, shows you the attenuation that's on the vertical axis against frequency, or wavelength, as I'll get to in a minute, on the horizontal axis. And you can see here two properties of fiber which make it very interesting to carry signals. First is the low attenuation. Attenuation there is given in decibels per kilometer, but basically the attenuation is very low. And this means that you can send signals a long way through fiber before they're greatly attenuated, many miles, up to 100 miles maybe. And that's quite different than wires. Now the other characteristic here is you'll look at the bands in which the attenuation is lowest, and there are these colored bands here at different frequencies which are used to transmit signals over fiber. Actually, I keep saying frequency, but by convention the horizontal axis is given in wavelength here. Wavelength is inversely related to frequency. So the wavelength is equal to the speed of light divided by the frequency. So that way you can relate the two of them. Now, in these bands, first of all, you see these bands, if you do the computations, you'll find that they run at very high frequencies. So we're not able to send signals literally. We need to use a carrier signal at higher frequencies to send information. And I'll get to that in a sec to give you the intuition. And moreover, the width of these bands, if you compute it in terms of Hertz, it's very large. We're talking about many, many gigahertz of bandwidth that's available to transmit signals over fiber in windows of low attenuation. That great bandwidth translates into being able to send information at very high rates, many, many gigabits per second. This is where the high capacity of fiber comes from. Okay, and wireless. What about sending signals across wireless links? Well, the principal difference compared to wires, or at least one key difference I want to point out to you, is that we need to send signals over wireless links using a carrier rather than directly. Here's a good old baseband signal, the signal we actually want to send that encodes the ones and the zeros. That signal can't be sent directly out an antenna for physical reasons. You need a very, very large antenna and a lot of power and so forth. So instead, higher frequencies, carrier frequencies, are the frequencies which propagate over wireless channels, and we need to use a carrier frequency to send information. What does that look like? Well, it's not as complicated as it sounds. The carrier is simply a signal which goes up and down rapidly at a certain frequency, the carrier frequency, and what we can do is change characteristics of it. Here I'm going to change its amplitude. And you can see what I'm trying to do there is change the amplitude to convey just that shape of the signal we wanted to send. So by looking at the envelope of the signal, I'll be able to work out what kind of information it is we're sending. And fiber also carries information, uses a carrier signal to carry information because we're sending at higher frequencies than at baseband. Okay, here is a second characteristic of wireless for us to look at, and that is that wireless signals are attenuated rapidly as they travel away from the source of the transmission. So here I have a diagram which shows you the signal strength on the vertical axis against distance. Spatial distance, we'll just consider a line on the horizontal axis. And I have 2 points of transmission, Tx for transmission, here at A and B. Now, for each of them, we transmit with a certain power level and the signal falls off rapidly as we go away, and this attenuation is proportional to 1 on the distance squared. The signals are going to be attenuated at least this rapidly as you move away from the source. You might wonder where that 1 on distance squared comes from. Well, it's physics. If you think about the formula for the surface area of a sphere, as a signal expands over a volume of space, that sphere has a surface area of 4 pi r squared. So the area of the sphere is increasing as the radius squared. That translates into the energy per unit area, if it's the same energy, decreasing at least 1 on the distance squared. And it's at least that because other mechanisms can cause the wireless signal energy to be lost. Now, don't worry about that. You don't need to really understand that. That's just if you're curious. The point I want you to take away is that wireless signals attenuate quickly, at least most rapidly from the source. The signal energy goes down very quickly. And a third characteristic of wireless which is important to us, and this is unlike wires too, where in wires the signal travels directly down that wire, and whatever we put on the wire we sort of get out the other end. Well, in wireless many people can be transmitting in different locations, and if they transmit, here we have our 3 transmitters at A, B and C. If they transmit on the same frequency, their signals will attenuate. Here's their signal attenuating, but they can overlap spatially. And this leads to a phenomenon called interference at the receiver. Let's just imagine for a moment that we have the receiver at another location, right here. I'll call this D if you like. What does D see? Oops, D, good grief, I'm just trying to write D sees. What does D see? Well, at this particular location, we can see that there are signals from all 3 transmitters are present at different amounts of attenuation. So actually, D will see a strong signal from C, and that's this up here, high here, and down here we have weaker signals. I'll just say a weak signal from A and B. Now D will see all of those signals together. It would be nice if they were all separated, but that's not the way it works. You see the superimposition of all of these signals. Actually, this means that D may have a lot of trouble disentangling them. In fact, it may be able to cleanly separate out to receive none of these signals individually because they're all messing up one another. And finally, the last characteristic, actually maybe not quite the last characteristic, but we're almost getting there, that I'll tell you about for wireless is what's called spatial reuse. And that has to do with this phenomenon of interference. So we talked before, this is the same diagram as the previous slide, and I said that, if we were at point D, we would see all of these signals overlapping. But if you look at the decay of these signals, you should be able to see, over at least about, let's say, this band and this band. Here, I should be able to send, within these regions, I can receive the signal B without the signal from A interfering. If I simply look at a point here, I get a fairly strong signal for B, and I get no signal that I've shown here for A. A signal continues to propagate and attenuate, but below about this level here, I just haven't drawn it on the graph because we consider it too weak to be picked up. Similarly, over here, you can see that within this region here, anywhere within the region that I'm showing here, A signal can be received, and the signal from B is not strong enough to really be noticed and hence interfere with that in a noticeable way. This means that we can reuse frequencies at these two transmitter locations, A and B. However, if you consider C, is C, a signal being transmitted, well, if we try and receive it at a point in the middle here, actually we get strong signals from both B and C, and they interfere as I've described in the previous slide. So that means for these two signals, C and B, no reuse. You can't cleanly reuse the same frequency at these two transmitters because they're closer together and their signals will interfere. So the notion of spatial reuse is that if the transmitters are far enough apart spatially, we'll be able to reuse and transmit information on the same frequency. Okay, well, you can see how wireless is getting kind of complicated. I'm going to stop telling you about wireless effects in just a moment. I really want to make two points and then one more effect. There's always one more to show you about wireless. And this is really to give you a sense of the complexity. So wireless is by far the most complicated medium in which signals propagate compared to the case of wires and fiber, really for two reasons. They're all the same basic electromagnetic effects, but two reasons here are getting us. One is that wireless propagation is very complicated because it depends on the environment. We're no longer just going down a wire, we're propagating in a complicated environment. So there are buildings that can get in the way and shadow signals, trees, signals can bounce off all sorts of things including the ground. The signals can be divided and recombined in interesting ways. And this makes wireless propagation a very complicated phenomenon because of the environment. And the other reason that wireless propagation is complicated is that many of the key effects depend significantly on the frequencies. Signals at different frequencies propagate in different ways. To use an analogy, light is a very high frequency, so it propagates in a very directional way, like shining a torch. Sound is a very much lower frequency phenomenon, and it does things like it goes around corners. You can hear people even when they're in another room. So a different frequency there can be related to very different physical effects. For us, some of the physical effects which will be most important will be those that happen in the microwave band. That's what's used for 802.11 and 3G cellular and so forth. And in a particular effect that I'm going to tell you about is multipath. We should care about multipath. Other than that and the other effects I've told you about, I'll leave it at the wireless propagation is complicated, but we won't really have to worry about any more than the effects I've already told you about. Multipath is important for us to understand because it has a big effect on communication systems. Multipath occurs because in the microwave band, signals bounce off objects. This means that they can take multiple paths between a sender and a receiver. On the left, here I have a transmitter, and on the right, I have receivers, TX and RX. Now let's just look at one receiver up at the top here. The signal from the transmitter is going to be sent out in all directions. Some of it might go directly to the receiver. Another bit of it might go in a different direction, but bounce off. A filing cabinet is the classic thing, and also arrive at the receiver. The receiver will then see two different signals that arrived over multiple paths. These signals will be superimposed, so they will add. Let's just say that we had one signal like this and another signal which was also going up and down just as fast. When we add them, we get this strong signal. It's not faded. Now, suppose that just because of the position of the reflector, the path, the same thing's going to happen down at this other receiver. It's going to get a direct one-on-one via this reflector. But now say that the path from this other reflector has a different length. It will. And in this case, the phase of the signals is going to be a little different. So I'll receive one signal, just like this as before. And the other signal, oh gosh, how can I draw this? I'm going to offset. It's the same thing, it's just shifted. The result when you add these things together is that these signals mostly cancel, and you get a faded signal here. This is called multipath fading. The effect is very difficult to deal with because it can change over very small distances. As I move just maybe even a few centimeters, my signal might go from fine to mostly gone. This effect is also frequency dependent. The result is that in wireless channels, often you're in data communications, often your signal is really quite messed up. It's missing portions of it because some frequencies were lost. We then need to handle it with fairly sophisticated communication methods. If you're interested in learning more, you can look in your text. In particular, there's a method that you'll hear about quite a lot called OFDM that's used. We're not going to have time to go into OFDM in this course.